There is something sitting at the edge of human understanding that doesn't just challenge our knowledge of space, it challenges our understanding of reality itself. Not a distant philosophical puzzle, not a theoretical thought experiment buried in an academic paper. Something real, something that exists right now. In the universe we actually live in, doing things to space and time and matter that nothing in your everyday experience prepared you to understand. And the strange thing, the part that I keep coming back to, is that the more we study black holes, the more they seem to be teaching us things that reach far beyond themselves. Things about the birth of the universe, things about the nature of time, things about whether information, the most fundamental stuff of existence, can ever truly be destroyed. Black holes, it turns out, are not just extreme objects. They are windows into the deepest and most unresolved questions in all of physics. And some of the answers coming through those windows right now are stranger and more beautiful than almost anyone predicted. That is what this video is about. Not a surface level tour of what a black hole is. You probably know the basics. Enormous gravity, event horizon, nothing escapes. What I want to take you into today is what black holes are actively revealing right now. Through some of the most extraordinary observations and theoretical breakthroughs of the past few years about the hidden architecture of the universe itself, let's start at the beginning, not the beginning of black holes, but the beginning of why they matter in a way that goes far beyond their own existence. There's a question that sits underneath almost all of modern physics, and it's a surprisingly simple one to state, even though it has resisted solution for nearly a century. The two great frameworks that describe how the universe works, Einstein's general relativity, which governs gravity and the behavior of space and time on large scales, and quantum mechanics, which governs the behavior of particles and energy on the smallest scales, are both extraordinarily successful on their own terms. Each has been tested thousands of times and confirmed to a level of precision that is almost incomprehensible, and yet they are fundamentally incompatible with each other. They use different mathematical languages. They rest on different foundational assumptions. When you try to apply both simultaneously to the same situation, the equations break down. They produce infinite answers, which in physics is always a sign that something is wrong, that the theory is reaching the edge of its domain and failing. For most situations in the universe, this incompatibility doesn't matter because gravity and quantum mechanics operate on such different scales that they rarely collide. But there is one place where they absolutely must both apply simultaneously, where you cannot choose one and ignore the other, where the mathematics of curved spacetime and the mathematics of quantum uncertainty crash into each other with no escape inside a black hole. This is why black holes are so important to fundamental physics. They are not just extreme astrophysical objects. They are the universe's own laboratory for testing what happens when our two deepest and most successful theories of reality are forced to confront each other. And what they're revealing in that confrontation is rewriting our understanding of the cosmos at its most fundamental level. To appreciate the depth of what black holes are teaching us, you need to understand what makes them structurally unlike anything else. When a sufficiently massive star reaches the end of its life and exhausts the nuclear fuel that has kept it burning for millions or billions of years, the outward pressure of that burning can no longer counteract the inward pull of gravity. The star collapses, catastrophically, violently, in a timescale measured in seconds rather than the millions of years of its lifespan. And under the right conditions, what is left behind is an object whose gravitational pull is so extreme that even light traveling at just under 300,000 kilometers per second cannot escape from within a certain boundary. That boundary is called the event horizon. It is one of the most extraordinary concepts in all of physics because it is not a physical surface. You cannot touch it. If you were falling into a black hole, you might not notice any dramatic change as you crossed it. There is no wall, no visible boundary, no physical material. It is simply a point of no return, a threshold defined entirely by the geometry of spacetime, beyond which the escape velocity exceeds the speed of light. And yet this purely geometric boundary, this line in the abstract fabric of spacetime, has implications that are among the deepest in science. Because once something crosses it from the perspective of the outside universe, it is gone. Its effects persist, its gravity remains. But information about its specific internal state, the particular arrangement of the matter and energy that fell in, is sealed away, and that sealing away turns out to be one of the most profound puzzles in physics. There is a problem so deep and so unresolved that physicists have been arguing about it for 50 years, and the argument is still not settled. It's called the black hole information paradox, And it originates with a discovery made by Stephen Hawking in the 1970s that initially seemed like a beautiful theoretical result and only later revealed itself to be one of the most troubling puzzles in all of science. Hawking showed, through a calculation that combined quantum mechanics with general relativity in a careful way, that black holes are not completely black. They glow very, very faintly, with a kind of thermal radiation now called Hawking radiation arising from quantum effects near the event horizon. This was a stunning and unexpected result. It meant that black holes slowly lose energy over time, radiating it away in this faint glow. And it meant that over an astronomically long time scale, a black hole would eventually evaporate completely, shrink, dwindle, and finally vanish. But here is where the problem bites. Hawking radiation, as originally calculated, is perfectly thermal. It is completely random. It carries no specific information about what fell into the black hole. So if a black hole evaporates completely and the radiation it emits contains no record of what it swallowed, where did that information go? Quantum mechanics has an absolute law. One of its deepest foundational principles is that information is never destroyed. The laws of quantum physics are reversible in time. If you know the exact state of a system now, you could in principle calculate both its future and its past with perfect precision. Information is always conserved. But if a black hole destroys information during evaporation, that principle is violated. Something has to give. Either Hawking's calculation is wrong or quantum mechanics is wrong, or our understanding of what happens at the event horizon is wrong, and figuring out which of these is where things get truly extraordinary. Over the past decade, some of the most creative and mathematically sophisticated minds in theoretical physics have converged on a set of ideas that are beginning to look like they might be pointing toward a resolution. And what's remarkable is where those ideas are pointing. They're pointing to a connection between black holes and something that seems completely unrelated. The nature of quantum entanglement and the geometry of spacetime itself. There's a concept in quantum mechanics called entanglement, which Einstein famously and somewhat dismissively described as spooky action at a distance. When two particles become quantum mechanically entangled, they share a kind of correlated existence regardless of how far apart they are. Measure one and you instantly know something about the state of the other, no matter whether they're in the same room or on opposite sides of the universe. Einstein was deeply uncomfortable with this because it seemed to suggest an instantaneous influence that violated his principle that nothing can travel faster than light. But entanglement is real. It has been experimentally confirmed countless times. What's remarkable is that in recent years, theoretical physicists have discovered what appears to be a deep and previously unsuspected connection between quantum entanglement and the geometry of spacetime. The pioneering insight captured in what's now known as the ER equals EPR conjecture, proposed by Joan Maldacena and Leonard Susskind, suggests that entanglement and wormholes, those exotic hypothetical tunnels through space-time that Einstein himself described mathematically, may be two descriptions of the same underlying phenomenon, that the fabric of space-time itself may be stitched together by quantum entanglement. That geometry and quantum information are not separate things, but aspects of a single deeper reality. Black holes are where this insight becomes most acute and most testable. And recent theoretical work has begun to suggest that the way information escapes from an evaporating black hole involves the interior of the black hole, becoming quantum mechanically entangled with the radiation it emits in a way that encodes subtly and indirectly the information about what fell in. The black hole doesn't destroy information. It encodes it in the correlations between emitted particles in a form so scrambled and distributed that reconstructing it would be effectively impossible in practice, but preserved in principle. The universe keeps its books balanced, even inside the most extreme objects it contains. And now let me take you from the theoretical to the observational, because some of what black holes are physically revealing to us through our telescopes and detectors is no less extraordinary than what they're revealing to our theorists. In September 2015, something happened that had never happened before in human history. Two massive black holes, each roughly 30 times the mass of our sun, orbiting each other at a substantial fraction of the speed of light, finally merged after billions of years of spiraling inward. And in the final fraction of a second of that merger, they released more energy than all the stars in the observable universe combined, in the form of gravitational waves. Ripples in the fabric of spacetime itself, ripples that had traveled over 1 billion light years, stretching and compressing space by a fraction far smaller than the width of a proton, and that were detected by an instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory on Earth. This detection was one of the most significant scientific achievements of the modern era. But what tends to get less attention than the detection itself is what we've learned since that first detection, the network of gravitational wave observatories has recorded dozens of black hole mergers. And together they have begun to reveal a population of black holes that doesn't fit neatly into what we expected. There are black holes in what physicists call the pair instability mass gap, a range of masses between roughly 50 and 140 times the mass of the sun, where standard stellar evolution theory says black holes cannot form, because stars in that mass range are destroyed by their own instability before they can collapse into a black hole. And yet LIGO has detected black holes in that range, which means either our understanding of how black holes form is incomplete, or these black holes formed through mergers of smaller black holes, implying a rich and complex history of black hole collisions we're only beginning to map. Each detection is not just an observation of an exotic event. It is a data point in a census of the black hole population of the universe, a census that is already revealing surprises. But the gravitational wave observations are not the only new observational window that has opened onto black holes in recent years. In 2019, the Event Horizon Telescope collaboration published the first ever image of the shadow of a black hole, the supermassive object at the center of the galaxy Messier 87, a black hole 6.5 billion times the mass of our sun. And then in 2022, they published an image of the shadow at the center of our own Milky Way galaxy. These images, produced by linking radio telescopes across the entire surface of the Earth into a virtual telescope the size of the planet, showed something that had previously existed only in theoretical calculations and artistic renderings, a bright ring of superheated plasma surrounding a central darkness. The shadow. The region where the black hole's gravity is so extreme that even the light from the glowing gas behind it cannot escape. But here too, what the image is revealing goes beyond its surface drama. Because in the years since its publication, theorists have been working to extract from the subtle features of that image constraints on the physics of the black hole itself. The size and shape of the shadow encodes information about the geometry of spacetime in the vicinity of the event horizon. Comparing the observed image to the predictions of general relativity is a test of Einstein's theory in the most extreme gravitational environment observable in the universe. And so far, it passes. But the precision of current observations leaves room for alternative descriptions, and the competition to build ever more detailed images of the black hole shadow is in many ways a competition to test general relativity itself in its most extreme domain. Let me now take you somewhere that I think is one of the most remarkable frontiers in contemporary astrophysics, and it connects what's happening at the largest scales we can observe with what's happening at the smallest. There is a class of objects scattered throughout the universe called quasars. They are among the brightest objects ever observed, outshining entire galaxies by factors of hundreds or thousands, and for decades after their discovery in the 1960s, their power source was a mystery. What could possibly generate so much energy from such a compact region of space? The answer, confirmed through decades of observations, is that quasars are powered by supermassive black holes actively consuming enormous quantities of matter. As gas and dust fall toward the black hole, they form a swirling disk of superheated plasma called an accretion disk, and the friction within that disk releases energy with an efficiency that nuclear fusion cannot approach. Black holes are the most efficient energy converters in the known universe. And in their most active phases, they release so much energy in the form of radiation and powerful jets of plasma moving at close to the speed of light that they reshape the galaxies around them. We now know, from extensive observational evidence, that supermassive black holes and the galaxies that host them grow and evolve together in a relationship so intimate and interconnected that neither can be fully understood without the other. The mass of the black hole at a galaxy's center correlates tightly with the properties of the galaxy's central bulge of stars. Even though the black hole is vastly smaller than the galaxy and its direct gravitational influence extends only to a tiny fraction of the galaxy's volume, this correlation is one of the most striking and still not fully explained relationships in astrophysics. And understanding it, tracing the feedback loop between the black hole's energy output and the star formation history of its host galaxy is one of the central challenges of modern cosmology. And I want to go somewhere even more extraordinary, into the early universe, because black holes are not only revealing secrets about the present cosmos, they are revealing something deeply puzzling about how the universe evolved in its first billion years. When we look at the most distant objects visible to us, Objects whose light has taken so long to reach us that we're seeing them as they existed when the universe was only a few 100 million years old. We find something that should not be there. Supermassive black holes, not small ones.